Quick question. If you wanted a drone to search a field for a missing person marker, how you would do that today? Most people would say open a mission planner, draw a bunch of waypoints by hand, upload that plan to the drone, hope nothing blocked the path, and maybe sit there with a joystick as a backup. That works, but it also means you did all the thinking. The drone just followed dots on a map. Now imagine a different vision. You type one sentence in plain words, search this field for the survivor marker, avoid obstacles, come home and land. And then something plans the search, flies it, looks around, hits a blocked path, tries another route, and lands, while you watch every decision appears as a tool call on screen. That second version is what this video is about. This is part of our new playlist, the Inspired by paper. I take a real research paper, extract the idea, and rebuild a small, honest demo you can actually run without pretending I cloned their entire lab setup. So here is a problem in normal terms. Drones are already good at flying. The hard part is deciding what to do next when the goal is messy and human inspect that roof, sweep the field, check if something is still there. Today, the decision layer is usually either a human with a remote or a pre-written program with fixed waypoints. Both are fine, both are also brittle. Change the goal slightly and someone has to replan it. Hit an unexpected obstacle and someone has to intervene. So researchers ask a natural question. Can we put a language model, the same kind of AI that writes code or answers question in the middle? So the mission is described in English and the actions are chosen step by step. That is the heart of the paper we are inspired by. Not AI magic flies a drone, more like can conversation become a control interface for a flying robot. So before we go further, there are 3 words you will hear in this paper and I will translate them or explain them in just a simple word so you never feel lost. First, language model, the LLM. You may be familiar with it, but think of it as a text brain. You give it a goal and some feedback, and then it suggests the next action in words or a structured command. In our demo, that brain can be a local model on your computer or a scripted stand-in for testing. The vision language model, VLM, that's a model that can look at camera image and answer a question about it in words. Like, do you see a red marker in this picture? Yes or no? The research paper uses a real one on real camera frames. In our demo, we faked that answer for teaching purposes and demonstration. Flight stack autopilot, that's the low-level software that turns go forward 3 meters into motor speed and stability. A popular open source one in the research is called PX4. You don't need to install it for this video, just remember it is the muscles and balance of the drone. The language model is trying to be the mission brain above it. One more acronym, MCP, the Model Context Protocol. You may also hear a lot about it. We had a small introduction video about the MCP and demonstration how to implement it. You can find the link of the video in the description below. If you have ever seen AI tool that can edit file or query database, you have already seen the idea. MCP is a standard way to say, here are named tools the model is allowed to call. Here are the arguments. Here is what comes back. In this project, the tools are not read file. They are takeoff, fly to a point, scan, and land. So the paper is called Taking Flight with Dialogue, published mid-2025. The authors wanted a natural language control of drones to be more open and accessible, not locked behind one company's API. In plain language, their system works like this. So you give a mission in wording. A vision model watches the drone's camera and answers simple question about what is in the view. Is the target here or not? A language model reads the answer plus the mission plus recent history and choose a small next move. Not a full flight plan for the whole day, just the next step. In their design, those steps were basically turn left or right by some angle, or move forward or back by a few meters. Those tiny commands go through robotics software layer called ROS2. Think of it as a wiring between AI and the autopilot into PX4, which actually flies the drone. They tested this in a high-end 3D simulator and also on a real custom quadcopter with an onboard computer, and they were honest about the result. The model were good at producing valid commands. The vision models were good at yes/no answers, but finishing full mission successfully was still hard. Their best combination succeeded about 4 times out of 10. So this is not solved product, it's an open research direction. That's exactly why it's interesting for us to teach and demonstrate. So now the honest part, because we are inspired by that paper, so I'm not running here any PX4 in this video or ROS2 or their big NVIDIA simulator or even a real vision model on a real camera. Why? Because that stack needs serious setup, GPU machine, robotics installed, hardware safety. Great for lab, but terrible as a first teaching demo. So I rebuilt the idea with demonstration friendly pieces. So the first one is we have a small world implemented in plain Python, like 60 by 60 meter field, a few obstacles like a barn or and a ball, a few hidden targets. One of them is a survivor marker we are hunting. The drone has simple physics: move, climb, battery drain, collide with obstacle. And the second piece is a real MCP server that exposes tools with the clear names: get the map bounds, take off, fly to coordinates, scan, land, read telemetry. The protocol is real, the tool description are real, and an agent can call them the same way it would call tools for your calendar or your repo. The third piece is an agent loop. For a clean demo path, I can use a scripted mock search, a lawnmower button, so you see a predictable flight. For a smarter brain, I can point it at a local language model through Olama on your machine. The fourth piece is a web console. So you can see the mission, map, 3D world, first person camera, live numbers, and every tool call as it happens. So what actually we mean by scan here? So it pretends to be a vision model. It retains something that looks like a vision answer, a name, a distance, direction, a confidence score. That is intentional. The star of this episode is the agent calling the tools and reacting, not a full computer vision pipeline. Later, you could replace that one function with a real camera and a real vision model and keep the rest. Same story for the flight stack. Later, you could implement the same tools against a real drone API. Takeoff still means takeoff. The agent doesn't need to know what changed underneath. So looking at the tool summary, an agent needs a menu of action it's allowed to take, clear results when something works, and clear failures when something doesn't. So when flight to this point fails because a barn in the way, the next decision should use that information. That back and forth decide, act, observe, decide again is the loop. MCP is simply a clean way to publish that menu. Same idea as giving cursor tool for your project file. Here the side effect isn't edit file, the side effect is the drone moved. So natural language is the mission, tools are the hands, the word simulated or real is what those hands touch. All right, so enough theory. So let's run the mission live. I'm going to press the start button. And while it flies, I will walk you through every part of the console, what you are looking at, what each move means, and what you would change if you want this closer to the paper or closer to a real project. So on the left side part, there is a drone agent workspace. Think of it as a home base for the console. Live mission is the page we are on. Across the top, you will see the status, and there is a stop button for the human override. The four cards are the telemetry, the position, altitude, battery, and mission time. We also have the toggle between the 2D and 3D, and we see the tool stream. This is the most important panel for learning. Every time the agent calls a tool, it shows up here with the argument and whether it succeeded. If you only watched the pretty map, you would miss why the drone moved. The stream is a why. So we have the option to start it with the Olama, and this is what I did here. But also we can start with a lawnmower, but a long leg back and forth, which is the classic way humans search an area when they don't know where the target is. It's just practical. So we see from the tool calls that we have something like a move to and scan. Move to is a request. So we need to go to the X and Y. If the path is clear, you either get OK and teal trail extended or no to check for another. Scan is a stand for look around with the camera. So in the teaching demo, scans return a simulated detection like a vision model would return. So we can practice the decision loop without building a full vision stack today. You should see a return toward home, the H marker and land tool call. Altitude should come down. Status move toward completes. Battery is lower than when we started, which is a tiny reminder that energy is part of the world model, even in toy simulation. So the teal path is the story of the mission in space. The tool stream is the story in time, and telemetry is the story in numbers. Together, they answer the question every supervisor will ask an AI system in a real world, like what did you do, why, and can I audit it? So the auditability is a big reason to put actions behind names and having these tool names instead of a black box auto mode button. You can replay the stream, you can see the failed move, you can argue with a specific decision. So let me summarize that. The paper showed a serious research path. Talk to the drone in spoken language, use a local model for eyes and brain, send small motion command into real autopilot stack, test in simulation and on hardware, promising and still hard. Full missions don't succeed every time. This demo keeps the idea and shares the packaging a bit for learning. So we have the plain text as a mission and agent that calls tools, MCP as a contract between brain and the world, mini simulated field so anyone can run it, a live console so you can see and audit what happened, a fake scan on purpose so we teach the loop before we teach the full vision. If we take nothing else, agents become useful when language can't touch the world through tools, and those tools must be allowed to fail out loud. Thanks for watching. If you want more of this, like the video, subscribe with the notification on, and share it with your friends. We release new videos every week on AI development, agents, and developer tooling. Thanks for being here.